All right, so we're going to prove this identity here, right? This sum of combinations and coefficients is equal to n times 2 to the n minus 1 for n greater than or equal to 1. Of course, we need n bigger than or equal to 1 because it's 2 to the n minus 1. All right, so here's the hint. We're going to expand n times 1 plus b to the n minus 1 using the binomial theorem, and we're going to let b be equal to 1. It also tells us to note this equality here. I'm just going to quickly showcase why this equality is true. So we have n times n minus 1, choose k, is equal to, so it's going to be n times n minus 1 factorial over k factorial, and then it's going to be n minus 1 minus k factorial. All right, so this is equal to, so n times n minus 1 factorial is n factorial. Then we have k factorial, and this could be written as n minus k minus 1 factorial. Okay. Okay, so we want to multiply top and bottom by k plus 1, right? Because we want the k plus 1 factorial here. So this is equal to k plus 1 n factorial over k factorial times k plus 1 times, and we can rewrite this as n minus k plus 1 factorial, right? Because in order to get the n choose k plus 1, we need n minus k plus 1 factorial, and n minus k minus 1 is equivalent to n minus k plus 1. All right, so this is equal to k plus 1 n factorial. K factorial times k plus 1 is k plus 1 factorial, and we have n minus k plus 1 factorial, and that is, by definition, k plus 1 times n choose k plus 1. So this shows why this equality is true. So let's go ahead and start the proof. Okay, so we're going to start with n times 2 to the n minus 1. N times 2 to the n minus 1. So we want to use the binomial theorem here. So this is going to be n times 1 plus, and of course in the hint they say b, but we're going to let b equal 1. So it's going to be 1 plus 1, right? To the n minus 1, and that corresponds with 1 plus 1 is 2, right? And then, of course, using the binomial theorem, this is n times the sum from k equals 0. It's going to n minus 1, okay? And it's going to be n minus 1, choose k, and it's going to be a, which in this case is 1, so 1 to the n minus 1 minus k times 1 to the k. Okay, so that's using the binomial theorem. Now, this is equal to, so I can, since this is n times this sum, n is going to be multiplied by each term in this series. So I can just put this n to all these terms in the series, right? So we can rewrite this as the sum from 0 to n minus 1, n minus 1, choose k, and then 1 to the n minus 1 minus k is still 1, and 1 of the k is 1 for all of these, right? So this expression is equivalent to this one. Now let's go ahead and use what we got, right? We have n times n minus 1 choose k, right? N times n minus 1 choose k, and that's equal to this expression here, right? So this is equal to it was k plus 1 times n choose k plus 1. right? And now let's go ahead and expand it, and it's going to show that the expansion is this here, right? So this is equal to, so the first term in the series is 0, so it's going to be 0 plus 1, n choose 0 plus 1, plus 1 plus 1, and choose 1 plus 1, plus 2 plus 1, and choose 2 plus 1, plus dot dot dot, plus, and then the last term in this series is n minus 1 plus 1, and then it's going to be n choose n minus 1 plus 1. And then we can rewrite these terms of this series as, so 0 plus 1 is 1, so it's just going to be n choose 1 plus 2 times n choose 2 plus 3 times n choose 3 plus dot 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 plus, so this case it's going to be n minus 1 plus 1 is n times n choose n, which is exactly what we wanted to show. We wanted to show that n times 2 to the n minus 1, right, is equal to this sum here, which is what we got using the binomial theorem.